Hello once again. I want to welcome you back to our lectures today. We will be talking about ethers and thiols, and ethers and thiols are just a very this particular lecture constitutes a much shorter topic, so we're going to be looking at all parts of both the ethers and thiols that we need to know. Everything we need to know about them will be done in this one lecture. Of course, I have some beautiful pictures for you there. This is a skunk. I'm going to come to why I have a skunk here. We're going to know the relationship between skunk and this topic. We're going to come to that. And then this is the structure of a dimethyl ether. This is methyl group, this is methyl group, and this is oxygen. So this is the commonest ether that we're going to see as we move on. Okay, let's take it off from there. As usual, I have a beautiful quote from for us. This time, this is a quote from a renowned congressman, a human rights advocate, and a freedom fighter who fought a lot for the society we live in today. He has fought a lot and made sure that we're living in a good society. He is John Lewis of the blessed memory. He just died recently, and think as at the time of recording this lecture, his funeral ceremony is still going on. I think so. So what is the quote? Let's hear from him. He said in this quote, "If you see something that is not right, not fair, not just, you have the moral obligation to do something about it." John Lewis. No wonder he has been referred to by his colleagues in the Congress as the conscience of the United States Congress. Let's immediately start our lecture. Learning objectives. Now, in this lecture, we have three things we need to cover. Number one, we will name and draw the structural formulas of simple ethers. And then we write the equations for the formation of disulfide when thiols undergo oxidation. And finally, we write the equations for the reformation of thiols again when those disulfide undergo reduction. So these are the three things, and we're going to look at a little bit of application of these with regards to heavy metal poisoning. So these are the things we're going to be covering in this lecture. Okay, let's immediately take it on from there. We'll start talking about the ethers. Ethers are compounds that contain carbon, oxygen, carbon functional group. When we say carbon, oxygen, carbon functional group, we're simply saying a carbon is connected to an oxygen and another carbon. So oxygen is usually at the center connected to two carbons. So you can, this carbon can be any type of arrow group, no matter the length. So two arrow group, just like we see in the general formula. Arrow group, arrow prime. Two different arrows, it could be the same or different, connected through an oxygen. The simplest member is the dimethyl ether. Like I told you, the dimethyl ether contains just two carbons. Is the simplest member of this family. So if I opened up that structure, it's just going to look like this. This is a methyl group. This is a methyl group, and then this is another methyl group. Of course, because this oxygen usually have two lone pairs, this is usually a bent configuration, of course, you know, but that is not part of what we need to know in this class. So this is the dimethyl ether. This is the full structural formula. This is the skeletal structure. Remember, in skeletal structure, any other atom except from hydrogen and carbon must be represented. All right, let's continue. So how do we name esters? Now, of course, we're going to see it as I move on now. The main focus of the nomenclature at the level of this class will be on the common names anyways, but I'm going to take a little peek at what the IUPAC nomenclature is. So the common names is easy. Now we name the groups that are attached to the oxygen. You name the two groups attached to the oxygen alphabetically. You have to number them off. Make sure that the alphabet that comes first had to be the first attachment name, then followed by the second one, and then lastly you add the word ether. The word ether usually comes at last when using these common names. The word ether has to be has to come at last. And now in IUPAC nomenclature, what do? In IUPAC nomenclature, we name the smaller part of the two arrow group, the two attachment, as an alkoxy group. Alkoxy group means if it's metal, we remove the YL and change it by OXY, it becomes methoxy. So we name the smaller of the two arrow groups, remember the two attachment, as an alkoxy group attached to the parent chain. The longer chain becomes the parent chain. So what you do is just replace the YLE from the alkyl group by OXY. So you take it from alkyl, this is alkyl group. When you remove YL, it converts to, go back to my red, ALK. You now put OXY. So that's what you now becomes alkoxy group. So what you brought in here typically is this, okay, let me use green, is this for alphabet. That's exactly how you do the IUPAC nomenclature. Like I said, we're not going to be spending a lot of time on the IUPAC nomenclature, like I already said it. So now let's do some nomenclature here immediately without wasting time. Now I have other few examples that I already named here. Like the commonest one I told you, these are when two methyl groups attach. There's a methyl group here, there's a methyl group here. Remember that? When the two methyl group, we call it dimethyl ether. Dimethyl because two methyl group is di, usually in two methyl group. So now if you want to name this in as IUPAC name, because both of them are the same chain length, so my longest chain can be, so I'm gonna choose one as my longest chain. So the longest chain will be methane. If this is my attachment, this becomes methoxy. If I want to name this thing, I'm going to say this one now will be my attachment. Okay, let me use a different color here to just illustrate that. So this is going to be my attachment to methane. So if that is my attachment, if I name it, then it's going to be, now the attachment is one carbon, so it's going to be methoxy. The long chain is methane. So this becomes the IUPAC name if you want to use that. Now let's go to this one. This is easy again. Two things attached. This is ethyl. Again, this is metal. Remember that this is metal group. So it's going to be E comes before M. So it's going to be ethyl, methyl, ether. Now if I want to name this by IUPAC, what do? The longest chain will be from here. No, sorry. This is from 1 and 2. So if this is 1, 2, that 2 doesn't look good. I'm going to, okay. Now what it means is if I want to name it now, this will be my attachment. So my attachment is going to be, now remember, if I'm going to name two of them as attachment, I'm not going to change this to what? It's going to be OXY, methoxy. So the name of this is going to be, now the attachment is methoxy. Now because it's just two, anywhere I put it, it's going to be 1. So you don't have to say 1. But if you want to say 1 methoxy, that's fine. But the best thing is not to put it because it's just it's short. Anywhere you put it, it's going to be 1. So it's going to be methoxy, not methoxyl. It's going to be like methoxy ethane because this is the longest chain. In this case, now the longest chain is ethane, 2 carbon. If we take out to this one too as well, this one I already named it. Now, if you count here, the longest chain I have here is 1. Let's see. 1. If you count from here, 1, 2, 3, 4. If you count from here, 1, 2, 3, the attachment becomes number 3 because this is the attachment. Remember, this attachment is ethyl group, so it's going to be ethoxy. That's no ethoxy, not ethoxy. This is ethoxy now. So that's why it is. So this what I have here is the IUPAC. Now remember, this is the IUPAC. This is the first one. So it's going to be, this attachment in carbon number 2 is going to be 2-ethoxy. The longest chain is 4, which is butane. 2-ethoxy butane. Now, if you want to name the common name, there are 2 attachments. This is the first R. This is the second R. You know. So the first R, this is ethyl. This is 1, 2, 3, 4. Because it was connected from number 2. This is actually isopropyl. No, not isopropyl. Sorry. Why did I do that? This is sec-butyl. This is sec-butyl, actually. So if you want to name this now, B comes before E. So it's going to be sec-butyl. Sec-butyl. This is ethyl eta. So this will be the common name. Remember, this is the common name for this guy. Common name for this. Alright, so this is how we do it. So the nomenclature, however, we're going to be focusing in this class is only the common name. If you see this in exam, if you see it in the problems, just give me the common name. However, I need to also add, there's also that importance there to introduce you a little bit of what the IUPAC name might look like. Now let's take this to the reflection questions and see what we've got. Now, in these questions, I'm going to be using the common names. So the question says, name the following using the common nomenclature. If I don't do this in the worksheet or exam, just go straight and give me the common name. So now we look for attachment and put eta. So this is 1, 2, 3, 4. So this is third butyl. Remember this third butyl. And this is ethyl. So it's easy. Third butyl comes before this. So it's going to be third butyl ethyl eta. That is how you name this. Now we go to this one. Now again, this is ethyl group. This is ethyl. And this is, remember, this is phenyl. Anytime you see an aromatic group as an attachment or benzene ring, it is phenyl. So which one comes first? E. So it's going to be ethyl, phenyl, eta. Remember, each of them in common name, eta has to be the last word. In this one now, this is ethyl and ethyl. Remember, this ethyl and ethyl. Both of them are ethyl. So you're going to use the word di. So this is going to be di, ethyl, eta. That's how you name this one. Easy. Again, this one, the same thing. This is isopropyl, 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 isopropyl. So we're going to say isopropyl, isopropyl eta. So that is how we name this one as well. Alright, so you see that easy cheesy. We now go to the next thing. You see cyclic Atos. Now cyclic Atos are heterocyclic ring. A heterocyclic ring is any ring which contains one or more atoms other than carbon. So when a ring is no more uniform, like if you have cyclohexane, remember this is a purely cyclohexane, it doesn't have any other thing. In a heterocyclic ring, it has other atoms apart from carbon. So that's what here we have. So in these specific ones, what it contains for this cyclic Atos is oxygen. So there are common structures with oxygen containing heterocyclic ring. If you look at this now, so there are two of them. This one is 1, 2, 3, 4. The one that looks like a 4 carbon here contains oxygen here. We call this the furan, whereas this one is the pyran. If you did this one 1, 2, 3, 4, this one has 5 rings, but oxygen replaces the other carbon. This is the pyran ring. Now the interesting thing about this is that many carbohydrates contain these fundamental ring structures. Carbohydrate, particularly the monosaccharide, exist predominantly as cyclic structures of either the pyran or the furan. That is the dominant structure, but most times you can draw them as open structure, which we call the Fischer projection. We're going to be doing some of these by the time we get into the carbohydrate. However, it's important that I show you an example. So now the predominant structure of glucose is usually drawn as a pyranose ring, which you see this is like cyclohexane. Now oxygen here is being replaced. So this is a pyran ring because it looks like this a little bit. If you see, it looks like this. So now if I add the other groups here, this is how you draw the cyclic structure of glucose. You don't need to memorize this for now, but in due time you're going to know how to do that. So this actually is called, because this OH group is facing downward, we say it's in alpha configuration. It's called alpha D glucopyranose. And look at the interesting thing. This pyran is coming from this because it looks like a pyran ring, and this is the most predominant structure. So like I said again, many carbohydrate containing compounds exist predominantly as these fundamental ring structures of furan and pyran, and that is an application of knowing these things, and we're going to go back to this in detail much later. Now, what are the properties of Atos? Of course, Ethers are much less polar than alcohols, and we have a reason. We can explain that. What's the reason? Okay, let me get this. Of course, if you look at the ether bond, let me just take the simplest ether, which is dimethyl ether. Of course, the electronegativity between oxygen and carbon is significant. Remember, oxygen is 3.5, carbon is 2.5. So when you subtract, it's about 1. So it's polar. So what that makes this to be partial negative, and this is partial positive. This is also partial positive. So what that means is that this has, from this way, there's a polar bond here, there's a polar bond here. That's exactly what this means. There's a polar bond here, and there's a polar bond here. So it's a little bit polar. But this polarity is not close to what you have in alcohols that have two strong polar, that the difference is much higher. Here, the polar bond here is much more higher than what you have here. That is why they are much less polar than alcohol. However, because they are polar, they are more soluble in water than the hydrocarbons. The hydrocarbons are the alkanes, the alkenes, the alkynes, and even the aromatics. They are much more, because those guys do not even contain any polar carbon at all. So the low boiling point and melting point, now they have low boiling point and melting point when you compare them with those of the alcohol. And the reason why they do that is because they cannot form hydrogen bonding with each other. In pure molecules of dimethyl ether, they can't hydrogen bond, and that makes sense, because if you have another of these, there's no hydrogen that is attached to this oxygen. Therefore, there can't be any hydrogen bond, and as a result, the only type of intermolecular forces they have, granted, is dipole-dipole, of course, and London dispersion force. And because they don't have hydrogen bonding, their boiling point and melting point will be low when you compare them with the likes of alcohol. However, it is greater than those of alkanes and hydrocarbons. Now, of course, they are inert and do not react with most reagents. However, they are highly flammable. What it means is that, like hydrocarbons, they can involve in combustion reaction, liberating huge amount of energy again. So this, like I said again, this is the space filling method of space filling model of I have it already. Space filling model of dimethyl ether, the simplest member of the family. So, like again, let me show you the structure. So, hydrogen bonding. There is hydrogen bonding of dimethyl ether with water. That is exactly why they are a little bit soluble in water, because they can form hydrogen bonding with water, but not with themselves. So they can hydrogen bond with water, and this actually makes lower molecular weight ethers to be soluble. Lower molecular weight ethers from C1 to about C3 are soluble in water. They're soluble in water because they can form hydrogen bonding with water, as we've seen. Remember, this is partial negative, partial positive, partial positive, partial positive, partial negative. However, beyond C3, which is from C4 and above, are insoluble in water. And the reason is because the longer hydrocarbon chain outweighs the possibility of solubility in water. Like I said again, they form hydrogen bonds with water. As we can see, this is the hydrogen bond it forms with water. Now, in their pure state, when you only have the same molecules of ethers, they cannot form hydrogen bond. And the reason why they can't form hydrogen bond is because there's no hydrogen attached to this, it's just a carbon. So they can't form hydrogen in pure state. And the significance of this is that because they don't form hydrogen bonding, they have low boiling and melting point. Of course, lower than those of the alcohols that do hydrogen bond in pure state. Now we're going to leave our thiols at this point. We're going to leave the ethers now. We're going to be talking about thiols. Thiols are sulfur containing compound. They are sulfur containing compound. Sulfur containing, and if you can see, I brought back my skunk picture. We are now going to be talking about that here. So the compound that contain the SH group, the SH group is also called the sulfhydryl group, the sulfhydryl functional group. Now, the most distinguished characteristics of this group of compounds, the thiols, is that they have strong and offensive odor, very offensive, very smelly. And the reason why it is smell is because when you see skunks, the skunks sting a lot. They sting and smell. And because they emit most of these thiols from their body. That is why the skunk themselves smell. And this beautiful skunk picture, I actually got it from Wikipedia. So let's see what happens here. Now, some common examples are ethanol is added to natural gas as an additive. Propanethiol is the odor of onions. You see how pungent the smell of onions is? It's because of propanethiol that it contains. Then other ones is a 1-propanethiol and 3,3-di 1-propanol disulfide. Is the odor you see and the flavor of garlic. You see this in garlic. You see that smell of garlic too? Not very, very pleasant. That is because of this particular compound. Other common ones are the trans-2-butene-1-thiol, 3-methyl-1-butanethiol, and other disulfide, which are the odors that are associated with the skunks. Like I said, that's why the skunk itself stink and smell unpleasantly, because they contain these, So we're not going to be dealing with the nomenclature, but a good way to name them is just to say the hydrocarbon chain and the thiol. So this is 1, 2. That's why we say it's ethanol. Very straightforward. Again, here the SH can be attached in carbon any number. So this is attached in carbon number 1. So if it's in carbon number 1, 2, 3. So this is propane, thiol. Since this is the carbon number 1, we say it's 1-propanethiol. Here the same thing. If you count again, 1, 2, 3, 4. This is an attachment which is the methyl group. So the methyl group is the carbon number 3, and of course this is the functional group, has to get the priority number 1. So it's going to be 3-methyl, 1-butane. This is the longest term, butanethiol. So that is how you name this. But however, it's not going to be part of what we're going to be doing in this class, actually. All right. So what are the thiol reactions? Our main focus will be looking at these two important thiol reactions and seeing their significance to biological systems. Thiols undergo oxidation. And when they undergo oxidation, they form disulfide. Disulfide is that you have two sulfur groups connected to each other. They form the disulfide linkages, or you can call them the disulfide bridges. Now, these disulfide bridges or linkages are important structural features of many peptides and proteins in the body. You know the role of proteins in the body. They perform a lot of the structural functions, the regulatory functions like hormones, and even the enzymes and all the rest of them. Most of these compounds are built by this link, which actually maintains their native structure. This disulfide bridge maintains the proteins and peptides native structures, and when those native structures are dismantled, they lose their functions actually. Now, so this is the general reaction. Let's look at the general. This is a general reaction. For that, this is the general reaction. In general reaction here, two thiols are being oxidized. When they are being oxidized, what happens? The two of them will now be connected into this disulfide bridge. This is the disulfide linkage or disulfide bridge. Disulfide bridge or linkage, whichever thing you want to call it. And then releasing a mole of water. In a general reaction, if you have two molecules of methanethiol combining, they form this disulfide compound and liberating one molecule of water. And again, I say, you find this disulfide in maintaining the structures of most proteins in their native state. Remember, for proteins, particularly the enzymes and hormones to function, they have to be in their native state because their structure is actually related to their functions. Now, other thiol reaction, we've talked about oxidation. Now, reduction takes it. Remember, the oxidation forms the disulfide. Now, when you now reduce this by reducing agent like hydrogen or other reducing agent, you get back this. So the reduction is actually the opposite of the oxidation when you begin to take this reaction back. Let's see. Now, so oxidation reaction can reverse the oxidation reaction. Oxidation reactions can be reversed by reduction with a reducing agent such as hydrogen or other reducing agent to generate the thiols back. So if we now, what do we do? Now this is in a general reaction like here. This is a general reaction. we have this disulfide. This disulfide, what happens? Is now being reduced by 2 molecules of this. So what's going to happen? This bond here is broken, and one of these hydrogen will be attached to this one, the other one will be attached to this one to form 2 molecules of your thiols here. This is exactly how this reaction occurs. And in a more specific one, here, look at what we have. This is like 2. Remember, this disulfide is made from 2 methane thiols. So what happens here? You cut this, take one of these hydrogen, one of them goes here, and the other one goes here to form your thiol. So reduction is just the opposite of the oxidation reaction. But remember, again, the oxidation reaction forms the disulfide, whereas the reduction reaction reduces the disulfide to the thiols again. Alright, so these reactions are important, and you need to know how at least to write these simple reactions. Now, still on thiol reaction, you see, thiols themselves react with heavy metals like lead, mercury, and cadmium to form insoluble compounds that have adverse biological effects on proteins, enzymes, and hormones. So many enzymes, like I said, contain these SH groups, which help to maintain their structures. Now, exposure of these enzymes to these heavy metals tie up these sulfide groups, making them to form stable molecules, rendering them ineffective. And this is actually the basis or the mechanism for heavy metal poisoning. Heavy metals, all the heavy metals that are dangerous, actually act by this mechanism. Look at what they do. Now, this is our methane thiol now, 2 molecules of methane thiol, which is normally supposed to undergo oxidation to form disulfide. Look at what they do. They come together. These molecules now come and act as that oxidizing agent. What do? They come and form a bridge between those 2 sulfides. This particular thing will now make the protein useless. The protein is going to be useless and without able to perform its biological function. Like I said again, this is the what? The biochemical basis of heavy metal poisoning. However, there is hope. Most heavy metal poisoning are treated by using chelating agent. Like lead poisoning can be controlled or cured by using the chelating agent, particularly EDTA. EDTA is ethylene diamine tetraacetic acid that is usually administered intravenously. What does it do? It goes there to claw out or mop out the lead and then convert it to product that is easily excretable through the kidney and reducing the toxicity. I have a beautiful picture for you here of the EDTA. Like I said again, this is the EDTA. It's called ethylene diamine tetraacetic acid, EDTA. Very long name, but it's easy. Look at what you have there. You have like, there's hydrogen here, there's hydrogen here to saturate this. This is the ethylene. So this is like ethylene, 2 amino group, diamine. Then this is acetic. Look, this is acetic acid. This is acetic acid, and there are 4 of them. So there is the 1, 2, 3, 4. That's why I say tetraacetic acid. So ethylene diamine tetraacetic acid. It is not your responsibility to know or to memorize the structure of this, but you can just even give me this name, that this is actually used in chelation therapy for the treatment of heavy metal poisoning, particularly lead poisoning. Alright, now another important application of the disulfide bond is seen in insulin. I just want to illustrate that. Like I told you that the disulfide bridge helps to maintain what? To maintain the native structure, or we can say the tertiary structure, but let me use the word native this time, of proteins, enzymes, and hormones, these proteins, because in that native structure is what makes them to be what? To be active. Actually, in this native state, if you destroy them from this native state, they're going to be useless. They can't perform their biological functions anymore. If they cease to perform their biological functions, that becomes a very serious disaster. So when this bond breaks as a result of either heavy metal or anything, it becomes a serious problem. I got this picture from Wikimedia, and it's from an OpenStax textbook as well. So these are those disulfide linkages that I talked about. You see how they maintain the structure of insulin is made up of 2 chains, the alpha chain and the beta chain. Both of them are linked together by, now this cysteine is an amino acid that contains the sulfur group. It's a sulfur containing amino acid, and both of these connections are done, the connection between the A chain and B chain are done through the cysteinyl residues, connecting them to maintain that particular tertiary native structure that makes insulin to function as a good hormone that controls the metabolism of carbohydrates. Now, the last but not the least of what we're going to be talking about here, still on the importance of this thiol, their biological function, is the hair palming process. What actually happens in the hair palming process? Now, of course, the hair itself, hair is made up of keratin. The hair itself is made up of keratin. Remember that. Keratin is a structural protein. It's made up of, let me show you. Keratin. Keratin is a structural protein, and of course it's also maintained by the hairs are maintained by disulfide linkages or bridges. Disulfide bridges again. Remember, these disulfide bridges are so important for most proteins to maintain their native structure. So what happens in palming process? In palming process, you want your hair to be beautiful. What happens in the first place is that, first of all, you apply a reducing agent, which goes to break those disulfide bridges and make your hair soft completely. And a good example of a reducing agent used here is ammonium thioglycolate, which comes to break those hair, break it down. And then when they are very loose and open, you move them around, put your jerry coil rollers and make them look that way. And what you do again, you now reoxidize them by addition of an oxidizing agent like hydrogen peroxide. So look at what happens. Now your hair, okay, there are two processes here. In A part, this is your hair. Your hair has at least some level of disulfide in them. Okay, so this is a disulfide linkage. There's a disulfide linkage again here that is actually maintaining it to some extent. Now in hair palming process, you want it to be loose. When you apply the first reducing agent, you want it to be loose. So what is going to happen? You apply the reducing agent. Remember, I told you the reducing agent is represented this way, but what usually the common ones applied is ammonium. Let me write it. It's ammonium thio. This is TH. Thioglycolate. Oh no, that didn't come out well. Thioglycolate is the reducing agent applied. So what happens here? It breaks those disulfide bonds or bridges. So what it does is that it converts it to sulfide groups. It just breaks it to SH. It just becomes, here I'm supposed to put HS again. Here it becomes SH. So you just break it down. Now when you break it down, what do? You now move them around. Remember, these are the disulfide bridges here. You break them into normal thiols and move them around the way you want them to look. Put your rollers of Jericho. Then after moving them around, what do? You are now starting from here. What you now do next is you now go from here and then do what? Apply your oxidizing agent now. Most of those oxidizing agents you use in those conditioning is usually hydrogen peroxide. They contain hydrogen peroxide as the oxidizer. So when you apply this, now what happens again? You are reforming this to look exactly the same way you have palmed the hair, the way you have packed your hair. So you are now going back to do what? To reform them again. So you are now reforming those disulfide bridges again. In this case, you are forming actually more of them. That is why your hair packs even more and better, and particularly staying the way you keep them and you carry them for some time. However, because the sulfides are highly susceptible to oxidation, they are highly susceptible to reduction. The disulfides are highly susceptible to reduction, even by atmospheric hydrogen. So by the time you get outside again and open your, you find out that it begins to unroll again because they have really been reduced again back to the thiol group. And after some time, you have to go back to the saloon and then remake your hair, reperm your hair again, and that is how the process and the cycles continue. And having talked about hair perming process, we've actually come to the end of this lecture. Thank you once again for listening. Bye at this point.